Welcome everyone to another Zoom into physics recorded in May 2022. I'll start by acknowledging the traditional custodians of the lands on which we're all meeting today online, and pay our respects to their elders past, present and emerging. And on the topic today of entropy, we know from the second law of thermodynamics that entropy always increases. So the traditional owners of the land must have been the lowest entropy inhabitants of the continent so far, and probably forever. This event is hosted by the Australian Institute of Physics, and the role of the AIP is promoting the role of physics in research, education, industry, and the community. Today, however, our Zoom into physics is on the topic of entropy. I have to say it's probably the stuff of physicists' nightmares when you're an undergraduate, but I'm sure people on this Zoom will disagree with that, and we'll have a really good conversation about it. I'm a little less scared of it than I was when we decided to do this topic, because I've watched lots of YouTube, which is what you do now to learn physics. You might notice a couple of particularly well dressed gentlemen on this call are endowed with towels, and that is in acknowledgement of International Towel Day. It commemorates the genius of Douglas Adams, who died in 2001. He's the author of The Hitchhiker's Guide to the Galaxy, and we demonstrate how awesome we are by demonstrating we really know where our towels are. As always, we have an opening question, which our panel answer when they introduce themselves, and we are a reduced panel this month. And this month our question is: does the concept of entropy lower or raise your temperature, and why? And so firstly, only two of our regular panel this month, and so I will get these hoopy fruits who really know where their towels are to introduce themselves. Firstly, Tibor.
Thanks, Scott. Yes, I'm Tibor Molnar, and I'm an associate of the philosophy department at Sydney University. And as a philosopher, I know absolutely nothing about entropy. Even though I studied physics many years ago, I don't think I understood it then, and I'm no expert today. So I'm really looking forward to finding out all about it from Geraint and from Luke. Does my temperature go up? My blood pressure goes up when I think about entropy. Particularly as I was just reading a little bit about free energy entropy, which totally confused me. So I'm looking forward to being enlightened.
Thank you, Tibor. And somebody who loves entropy, Geraint Lewis.
Oh, yeah, thank you. Yeah, so I'm a cosmologist at the University of Sydney. And in reality, I probably know about as much about entropy as Tibor does. It is one of those mystical topics in physics. I do have a bit of a grasp of it, and I do think it's an important thing. Does it get me heated up? I think I get heated up when I hear other people discuss entropy. I think I know what's going on with entropy, but other people, they seem to be very confused. And I just point out, with regards to towel, I have my travel towel with me. This is what I take everywhere. I always have a towel with me.
Very good.
Very well aligned with hitchhiking. And our guest panelist tonight is Professor Luke Barnes. Luke also loves entropy, I think, and it's very fitting for Towel Day that he's with us, because he, along with Geraint, have literally written guides to the universe for hitchhikers and everyone, in fact. Luke is a lecturer in astronomy and cosmology. He has a PhD from the University of Cambridge. He's published papers in the field of galaxy formation and the fine-tuning of the universe. With his co-author, Geraint, he has published the book entitled A Fortunate Universe, Life in a Finely Tuned Cosmos. And His research examines the link between life and the fundamental properties of the universe, so perfect for the topic tonight. So Luke, please say a little bit about yourself and answer the introductory question.
I think you've said enough there. You've promoted me to professor, so that's lovely. I'm a lecturer, but I'll take professor for today. That's fine. These views don't represent Western Sydney anyway, so that's great. Yeah, so you've given the introduction there, astrophysics and cosmology, and a whole lot of fun there. And again, yeah, I've just come off giving a set of lectures to some undergrads, 10 lectures on thermodynamics, including the second law of classical thermodynamics. So I'm very excited about entropy. I love it.
Great, thank you very much, Luke, and welcome. So let's kick off as we always love to as scientists with definitions. There are different types of entropy. That's something that we've learned during the preparation for this evening. We'll move on to the other forms of entropy later on, perhaps, but we'll focus on thermodynamic entropy at the moment. But would someone like to kick us off with a definition?
I'm happy to jump in just to give a starting point. So the entire notion of entropy, this quantity, it comes about because of the Industrial Revolution, right? So people, I guess, before steam engines knew how to handle animals, right? You feed them, you work them, and that was just a natural thing to do. But once people got steam engines and engines that run on non-animal power, there was a question of efficiency because it was related to money. I mean, how many tons of coal do you need to buy to run an engine to do so much work? And the entire field of thermodynamics grew out of this notion of trying to understand the efficiency of engines. And thermodynamics means the movement of heat. Right? So you move energy from one place to the other. Can that be done perfectly, or is it always a process in which there's going to be a loss? So it was realized that efficiency is never perfect. There are always losses, and the notion of entropy, at least thermodynamic entropy, comes from this realization that you're always going to lose useful energy. That any way you start off where you've got concentrated energy in the form of coal or wood, etc., when you run it through an engine, you're not going to be able to extract all that energy. Some will be lost. And the way you encapsulate that loss is encoded in this concept of entropy. So it's the fact that things are not efficient and the fact that things are always essentially running down, that you are wasting energy, that wraps up this concept of entropy, at least in its simplest form.
Which of course explains why you can't have perpetual motion machines.
Yes, that was one of the main findings of thermodynamics, is that there is no machine that can perfectly use the energy that comes into it. There will always be losses, so machines must always run down and stop unless you put more energy into the system.
So Geraint, what's the relationship between entropy and something I remember from high school, which is a Carnot cycle?
Well, the Carnot cycle, as devised by Sadi Carnot, who was working, I think back in the early 1800s, he was one of the first to consider what you need to do to extract energy, right? So he realized that you can't just have a magical process where, energy flows from one place to the other. And as we know now, engines have cycles to them. What we do is we compress and we expand, and et cetera, et cetera. So there is a cycle whereby you have an energy source, you have an energy usage, and that cycle effectively pumps energy from one place to the other. And what Carnot realized, and again, all part of this bigger topic where there are many great names of physics, is that process where you've got this cycle, right, means that you have energy in, energy out, and it's not perfect, that there is an energy loss. Effectively, what it boils down to at the end of the day is that there is a maximal efficiency that you can expect from your engine. Given an initial temperature and a final temperature, there's an efficiency, and you're not going to do better than that. So that sets limits on what you can do with the movement of heat, which is like the ultimate way of powering a system.
Yeah, does the area inside the graph of the Carnot cycle, I remember it's a kind of diamond-shaped thing on a graph. Does the area or the shape of that curve represent something to do with entropy? Do you get a mathematical relationship between those two, or are we talking about two different concepts here?
Well, I'll defer to Luke, who just finished teaching thermodynamics, to remind me exactly what the area of the Carnot cycle corresponds to.
So here's the problem. I have an 8-hour answer ready in my head, and I can take us through all of this. Okay, so the plot you're thinking of, which you may have vague memories of, you imagine, let's take the simplest sort of system that we can get a handle of and change some things and actually see what happens, which is have just a sample of gas and then a piston that can compress the gas or expand to allow the gas to expand. And what's amazing about that, what's extremely useful about that, is you only ever need two numbers to specify the state of the gas once it's arrived at some equilibrium state. When things have stopped moving around, all you need is the pressure, this gas, and classically we don't even know how, the gas can somehow exert a force, that's pressure, and volume, just how much space it takes up. The Carnot cycle is, if you map out the way you're going to allow this thing to move around, there's a cycle around that, put volume on the x-axis and pressure on the y-axis. There's a loop, because you go back where you start. The area inside that is actually the work done by the mechanical work done. The genius of that particular cycle from Carnot, it's a wonderfully subtle argument, but the genius of it is that the classic stereotypical best example of an entropy increasing process is when you take two things with different temperatures and you put them in contact with each other and they come to the same temperature eventually. Mm-hmm. That is always irreversible. Like, I can sit around all day with my cup of tea that's now come to room temperature, and it'll never pump heat back out into the room. Sorry, sort of draw heat in from the room, and get hot again. Yeah. The genius of the Carnot cycle is it's the engine, it's the way to run an engine with a simple piston, where it's never the case that two things with different temperature are in contact with each other. You allow it to expand at a constant temperature, and then you isolate it so there's no heat exchange, and then you allow it to expand. Anyway, the details are there. The genius of that is because you've avoided that classical irreversible process where two things are in different temperature in contact with each other, you've got then the most efficient engine. And so the number you can put on that is how efficient is this most efficient engine, and what characterizes the state of what the engine is doing in a way that is constantly increasing. That leads you via a beautiful, and if you've got a few more hours, let's go through this, a beautiful set of reasoning up to the idea of entropy.
Right, okay. Well, I'll defer until later the question of how do you get entropy out of all that. It'll take a while.
Well, I think that's a good question. I mean, I fully accept everything that's been said about efficiency of engines there. But yeah, what is the entropy in that? Where does entropy come out of that? Or
okay. Again, look, I'll jump in boots first, and I will start with the statement that entropy is a rubbery kind of thing at some level, because there are definitions of what is entropy, but there's more than one definition. So you can either go with the definition as laid out by Boltzmann, the famous physicist from the 1800s, or Gibbs, but there are other definitions of exactly what entropy is, how you would measure it with this, with a system. One of the first one was by Clausius. And so he basically defined the change in entropy to do with the flow of heat at a particular temperature. So if you have any kind of system whereby heat is flowing from one place to another, then you get that entropy is increasing. And the question is what that entropy means, what it is that it's relating to. And of course, there's this standard talk. Everybody says to you, oh, it's something to do with disorder. And every time I hear the example of somebody goes, oh, your child's bedroom can be messy or tidy, and that's related to entropy, I cry a little bit. But in my opinion, I think the best definition is about how much energy can you extract from a particular configuration, a particular situation. That is the guide to what entropy is telling you. Low entropy means that you have sources of energy you can tap. Maximal entropy means that even though you've got energy there, you can't tap that energy.
So, and look, I've just published the results of the of people's awareness of entropy here. So, quite a few people with high school understanding. So, the unit for entropy is joules per kilogram or joules per kilogram per mole. It seems if you're a chemist. Can anyone explain, Luke or Geraint, where that derives from and what does it actually mean?
It's joules per Kelvin, isn't it?
Oh, Kelvin,
Yeah,
sorry, Kelvin,
yeah,
sorry.
yeah.
Did I say kilogram? Sorry.
Yeah.
Yeah, Kelvin.
So again, the way you start off with, you work up, there's two laws before the second law. The first one is the first one is the zeroth law. We got them out of order historically. The great example of why logical order and historical order aren't always the same thing. The zeroth law of thermodynamics says, basically it says that equilibrium is universal. That if system A is in equilibrium with system B, and system B is in equilibrium with system C, then system A is in equilibrium with system C. So it transfers its way along. And by equilibrium, we can sort of nail that down to very observable terms. If I have my piston and my gas, and I do something, and I put this piston in contact with something else, and it does nothing, right? In thermal contact, nothing changes. Then they must have been in equilibrium with each other already. The second one is that the second one is now the first law. Sorry, let me just not use those terms. Okay, there's the zeroth law. Equilibrium is universal. That allows you to have a temperature scale. There's one number that you put on a system to tell me whether anything else with that same number, whether when you put them in contact, any heat will flow between them. The first law says that basically energy is conserved and heat is a form of energy. So using the idea of energy from Newtonian mechanics, of work done and forces pushing things around, we can quantify the amount of energy flowing around in a particular process. And when we take heat into account, even though classically we don't know what it is, we can still put a number of how much energy, how much heat is flowing around. Entropy is then the sort of classical definition where you don't even know what heat is, but you can put a number on this idea of entropy. Is a small amount of entropy change is associated with a certain amount of heat flowing at a certain temperature. The higher the temperature, the lower the entropy. So it's a small change in heat, a small amount of heat flowing divided by the temperature that it flows at. And what's remarkable is that well, when you've defined that quantity for any you can then use that to define something called the entropy at every point of the possibility space of how you could arrange your system. When with the simple gas cylinder there, it's just pressure and volume, as I said before. For any two of those, once you've done all your work, you've done your experiments, there's some function that turns pressure and volume into entropy. The remarkable thing about it is once you've learned to calculate this thing, even though it's not entirely clear what a change in heat divided by a temperature is, a little amount of heat flowing divided by a temperature is, it's the thing that allows you to say for any process, for any way that you could move around the set of possible arrangements of your system, this one's going to happen spontaneously and the one in reverse is not going to happen spontaneously. Anyway, the fact that the entropy is adding up little flows of heat divided by temperature means the units always have to be whatever your unit of energy is divided by whatever your unit of temperature is. So that's how we arrive there. Again, it's such a beautiful but slightly convoluted argument. You sort of get somewhere and you have to really think hard about what on earth this thing you derived is. A little amount of entropy, a little amount of energy flow in the form of heat divided by the temperature at which the energy flowed. What that means roughly is, so take the stereotypical example. I've got two things with different temperatures and I put them next to each other and heat's going to flow. It flows from the higher temperature to the lower one. So as you add up these different contributions, the entropy increases because the heat is flowing from a higher temperature to a lower temperature. So because it goes like 1/T, that means the entropy increases.
Okay. Yeah.
Can I add in a comment that that'll hopefully help understand this? I guess many people think that the most important quantity in running the universe is energy. Right? We all know that you need energy to do stuff. But that's not strictly true. The thing that matters is differences in energy, right? So you need gradients in energy for things to happen. And one of the examples that somebody explained to me a long time ago, which I think is very useful to think about, is that there's a massive, massive reservoir of energy in the sea, right? The sea is roughly 20 degrees centigrade around the world. And so if you think about the amount of water that there is, and then it's water at 20 degrees centigrade, and you calculate how much energy is in that water, there is a massive reservoir of energy. So why can't we just dip some wires into the ocean and extract that energy? And the reason is that the only way you can get energy to do stuff is if you get energy to flow from one place to another. And for the ocean, what you need temperature gradients. You need cool land and warm ocean, and that's where we can talk about extracting energy from the ocean, or places where that generates wind flow, etc. It's energy flow is the thing that is important in the universe, not just energy. And the entire thing about entropy is that entropy is related to the flow of energy and how that can't be perfect, and how that loses energy into wasteful energy. So yeah, entropy is associated with how much work can we extract from any energy source that we have, and energy gradients are the important thing.
Okay, that makes sense. So let's go back to order and disorder, because a lot of people talk about order and disorder. And Ian has made the comment, my understanding is that the cycle, e.g. Carnot, is only irreversible on a statistical basis. Running in reverse would not violate any basic micro laws. And so this is, I think, about the number of states that are essentially the same. And there are very very many states which are essentially indistinguishable and disordered, but very few that are quite specific. So,
am I allowed to comment again? Sorry,
oh yes, please do. Yeah.
No. Okay. So look, we are almost getting to one of the most deep and fundamental issues to do with the notion of thermodynamics. As I said, it came from the Industrial Revolution, but it is different to an awful lot of the rest of physics. And I had to write about this today. So the example I will give is, imagine you've got two electrons. So everybody hopefully listening knows that electrons are fundamental particles and they're charged particles. So they both have the same charge, so they repel. So if you imagine you've got two electrons and they are hurtling towards each other. I'm going to try and do this. I'm trying to see myself on my own camera here. Here we go. They are hurtling towards each other. They repel each other. They're going to slow down. They're going to stop. And they're going to repel. They're going to go in the opposite direction. And everybody's happy with that, right? So we all understand two charged particles come together, they repel. Now, if I filmed that process, okay, and I showed you the film, and I said, I flipped a coin, and either I'm showing you the film as I made it, or I've reversed the film. So you've seen it backwards. Can you tell it apart? And of course, no, two charged particles coming together and repelling. If you reverse it, looks like two charged particles coming together and repelling, right? So it turns out that in terms of fundamental physics, that there is this lack of appreciation of a direction of time. They are symmetrical in time. And this was realized a long time ago that this is one of the key things. The problem is that when you go to thermodynamics suddenly imprints a direction of time on your physics, because we've already spoken about the fact that we're talking about running a heat engine, and that heat engine is losing energy. Its efficiency is not perfect. And that energy is radiating off into the universe. And as Luke said with his cup of tea, energy isn't coming in from the universe and being sucked into his cup of tea and warming his tea up. So inside the laws of thermodynamics, there appears to be an arrow of time, which is not in the rest of the fundamental laws of physics. And physics has struggled with this notion, right? Because we know, as human beings, we know the difference between the past and the future. We know that a cup of tea cools down. We know that if you drop an egg, it smashes and makes a mess. And smashed eggs rarely suck themselves together and leap back onto the table. And this has been one of the big physics and philosophical discussions of the last century and a half now, is why thermodynamics has an arrow of time, yet fundamental physics, which underwrites thermodynamics, doesn't. And this is why we start to talk about entropy instead of the individual interactions. Like if you were talking about a gas, you talk about, oh, this molecule is going to bounce off that molecule, etc. We need to talk about a different aspect of the physics, and that's the way that situations evolve from one moment to the next. And I think Luke was getting at this, is that, you know, what we're talking about is that that the growth of entropy is essentially a change from a least likely situation to a more likely situation, in the sense that we start off with energy being concentrated, right, useful energy in coal or something like that, and becoming useless energy once we burnt the coal, such as soot and ash and infrared radiation. So that's the kind of evolution that we've got, and quite how fundamental physics and entropy are related is still a bit of a messy topic.
As I understand it, Geraint, somewhat simplistically, if you've got two elementary particles like electrons bouncing off each other, then there's not a lot of places for the energy to be or to go, because you've only got two particles and they've got to share the energy. The distribution of energy is an emergent statistical effect or a macroscopic effect. So you need a lot more particles than just two. And it's a localization of energy, or it's a distribution of energy thing that gives us our arrow of time or our entropy or something. Because if I imagine lots of particles, all very energetic in a confined space, then provided the box is completely sealed, then entropy or the amount of energy will stay inside the box. But if you don't have a box and these particles can fly off in all directions, then you no longer have enough energy in that localized space, and that you had less energy than you had before, and hence the energy of Luke's cup of tea or so goes down, because some of the more energetic particles evaporate out of the cup or something. So the direction of time and the arrow of time and the direction of entropy increasing and so on is really just an emergent effect. I don't see that as necessarily mysterious. Is there something more mysterious to it than that?
Yeah, when I think about it, I think of gas inside of a box.
Mm-hmm.
So if it's all the gas molecules inside the box to be somehow confined to one corner of the box, then the chance of that state being is very small. And over time, the molecules are going to move around and slowly emerge to spread all around the box. And the number of states, or the number of permutations that would, the number of states where the molecules will be evenly distributed throughout the box. There's a lot of states, there's lots and lots of different arrangements for the molecules to be in, for there to be an even distribution of molecules throughout the box. So therefore, the chances of a nice distribution throughout the box is high, and we're most likely to be in that state. And so, yes, I think the arrow of time is statistically emergent. It's not impossible for the thing to run backwards, but it's very, very, very unlikely.
I'm going to agree that two individual gas particles don't know about entropy and don't know about temperature and don't know about density, right? And then when you go to a macroscopic picture, you have temperature, heat, and energy, and you can talk about that as a description of an ensemble of lots of individual particles. The question of whether or not it's an emergent thing, I think, is rather messier. I'm going to hand over to Luke now, because he likes to talk about this, about the example that was just given there about entropy. If you start off with gas in the corner of a room, gas in the corner of a room, and you let it go, it's going to basically spread out and fill the room. And so you go from low entropy to high entropy. But if I instantaneously froze time and reversed the directions of every atom and then played it forward after I've reversed the velocities of every atom, then what's going to happen is that they're suddenly going to converge down to the corner of the room. Right, so I can do that. I mean, I just have to reverse every picture, every velocity, and I will recreate the initial conditions. So it's not quite as simple as saying, oh, gas will always go from the corner of the room to filling the room. There's a deeper story there. And so Luke, over to you.
Yeah. Okay. So what's been said so far can't be the whole answer, and here's why. What Geraint just said was there's some way of describing where every single particle is and where it's moved, which describes all the particles spreading out over the box, right? And so there's that set of trajectories, all right? Keep that set in mind. What Geraint said was, if I take that set of trajectories at any time and just reverse all the velocities, so if particles going this way, just send it back the other way, Now you've got a set of trajectories which starts off in a spread out gas all over a box, and then at some point, spontaneously, everything in the box just jumps up into the corner. And so you've got a perfectly good solution for a box of gas spontaneously jumping over into the corner of the box and leaving the rest of the gas as a vacuum. Here's the problem. Those two trajectories, I can put every trajectory where things do what we think they'll do and spread out. There's a one-to-one relationship between that normal trajectory and one of these backwards ones where everything jumps up into the corner. There's one of each. And if you're looking for the fundamental laws of nature to tell us that the spreading out one is fine, but the contracting one is not fine, that's not what the fundamental laws say. They say, oh no, they're both fine. I don't care about the direction of time. So there's got to be something else going on here. And it can't just be mere statistical averaging, because what does the universe care about statistical averaging? That's something we do. You can't tell me that the process of taking an average is what causes my teacup to cool down, right? We're not doing that. The laws of probabilities and statistics, they don't know about the direction of time either. If there's something in this situation that tells us why in our universe we see the gas spreading out, but not the one in reverse, it's not in the fundamental laws, and it's got to be something other than the statistical averaging. The statistical averaging is perfectly correct as far as it goes. The real problem with that argument is it works perfectly well in either direction in time. So let's take an example of, let's take the gas in the box, always talking about gas in a box. It's our favorite thing if you're a physicist. Suppose that we take a photo, and it's we have the state of the box at one time, and we see that half of the box has gas in it and the other half doesn't. We've taken a photo, and you say, okay, that's all you know about the box. On average, what's going to happen in the next 2 seconds? And we do the statistical averaging thing, and it works great. And that says that the gas is going to spread out over the rest of the box. And lo and behold, whenever we do this experiment, that's all great and wonderful and fine. Here's the problem. Start halfway again and just use the fundamental laws and this idea of statistical averaging and say at time t, the gas was in half of the box. Where was it 2 seconds ago? Because everything in that argument, remember the correct argument that said it spreads out, because everything in that argument was time reversible, you have to give the same answer. You have to say that if the gas is in half the box, then 2 seconds ago, it was filling the whole box and spontaneously jumped to fill half of the box, which is the wrong answer. Well, for a lot of the applications here, it'll be the wrong answer. If I put some ice in a glass and I let it melt over the course of half an hour, and I say halfway through there, 15 minutes in, what happens next? Statistical averaging, laws of nature, great. The ice will continue to melt, wonderful stuff. But if I ask, okay, it's now 15 minutes in, what was the state of the glass 15 minutes ago? I have to give the same answer, because if I'm only relying on statistical averaging and the fundamental laws, what that's telling us is that there's something else. We have to say something about the initial conditions of the universe if we're going to understand the second law. We have to say, this is called the past hypothesis, that the entropy of the universe was very low at the beginning of the universe. That changes the entire thing, because now I'm not saying, okay, it's 15 minutes in, the ice is half melted, where was it 15 minutes ago? I'm now saying, where was it 15 minutes ago, but 13.8 billion years after the Big Bang, which was a low entropy condition. And if I ask that question, then I get the right answer, that it was fully melted 15 minutes ago. But this is the line of reasoning. We're sort of all repeating some arguments that Einstein and a whole bunch of other physicists went through 100 years ago. These are called the reversibility objections. And they lead to the understanding that you have to put in a low entropy initial condition if you're going to understand the second law.
Yeah,
I have shocked the crowd.
yeah. Can I just jump in? I mean, I think this is important in the sense that every time you're having a gin and tonic with ice, you have to remember that the fact that you're having a gin and tonic with ice which is going to melt is something to do with the initial conditions of the universe. So I tell myself that every time I have a gin and tonic. I mean, that's the most important aspect of it.
That's a very good reason for being a cosmologist, I'm sure.
Yeah.
Look, is there a, I'm going to use the wrong word here, is there a combinatorics or something thing going on here? What I'm thinking about is, if I have a gas in a box and say it's got some finite number, say 1 million air particles or molecules or something in it, and they're all whizzing around randomly in some sort of pseudo Brownian motion or something, they're just randomly whizzing about, and there's a certain temperature and it's in equilibrium or something. There are, you can describe, you can write down in a very long equation, which is 1 million times, I don't know how many, different states that gas can be in that box. In other words, one can be moving to the left and all the others are moving the other way, or you could have two moving, and so you can add them all up. You have a gazillion states that the thing can be in. And presumably that's a finite number as well. It's just a very, very large number. It's some factorial of who knows what. But if we have that many different states that the system can be in, or dynamic states, because they're all velocity and position descriptions. If we have that, now if we have your half melted ice example, or particles in half a box or something, in that kind of semi-state, if you describe all the different states that it can be in and all the reversible states that they can be in, are there an equal number, or is there a fewer number? Is there a smaller number of states that will make all the particles go back into half the box than there are number of states that will make it go and spread out all over the whole box? Is there a numerical combinatorial kind of difference going on there?
Yeah, so this is Boltzmann's ideas of entropy. So here's perhaps the best way I can explain it. So think about, again, particles in a box again, because why not? So there's something called phase space. And what it is write down to specify the state of the box. Tell me everything you can tell me. Let's just do this classically, ignore quantum mechanics for the moment. But to tell me everything about the box, the state of the box right now, you've got to tell me where every particle is, so 3 numbers for that, and the velocity, so 3 numbers for the direction it's moving and the speed it's moving. And if you do that for all the particles, you've told me everything. And what we could think of is, if there's n particles in the box, I need 6 n numbers to tell me everything. And then I could imagine, well, I can't really imagine, but at least mathematically, we could think about plotting that in a 6n dimensional space. And so the state of the system is just, there. So what you can then do is to say, okay, what do most of the states look like? What does it look like if you just go exploring around this phase space? And the answer is the vast majority of those states look like gas which is spread out all over the box and has the distribution of velocities and speeds that we associate with thermal equilibrium, so that the box is uniform, distributed, it's not all over on one side, and it's all at the same temperature. And the vast majority of states in phase space, the vast majority of ways to arrange, every particle's, position and velocity, look like one of those states. And so you think you've almost got the answer here to the second law, right? So if I start the system off on one side of the box, surely it's going to, if it just then moves randomly through phase space, it'll probably end up in one of those overwhelming majority, which looks like the boring gas all at the same temperature spread out all across the box. The problem is that under this, sort of behind the scenes, in the actual trajectories through phase space, so as the system evolves it'll move around through phase space. You know, this particle collides with that particle, and suddenly they're in different places and different velocities. So the phase space moves around. The problem is that for every trajectory that goes from here in phase space to there in phase space, there's another one, always, you know, one-to-one correspondence, but for a trajectory that goes backwards, goes the other way around. The key to this is that most of the states that are in equilibrium are not just in equilibrium, but they are not the kind of equilibrium which was out of equilibrium 30 seconds ago, right? So there's the state, if I take, you know, the gas to half the box, let it go, you know, 10 seconds later, it's all spread out all over the box, great. And if I look at that state, it'll be just somewhere in the mix in phase space, but it's actually quite a special place of phase space. You could take all of those points and say, how long ago was it, if I follow that trajectory backwards, how long ago was the gas over in half the box? And what's special about the equilibrium systems we see around us, where the universe has reached equilibrium, is that they're not just the typical ones where they're in equilibrium and they've been in equilibrium forever, and it's a squazillion times the age of the universe since they've been in half the box. The ones around us are the ones where, yes, the air in this room is in equilibrium, but if we trace it backwards in time, we find that it goes to lower entropy states recently. So the special thing about the half melted ice, right? If you go look in the phase space of that system, right? The glass, ice, water, and you say, you know, what does the typical thing look like? It just looks like tepid water, typical space. All right, look at all the ways you can get to a half melted ice. Most of them, if you're just looking at phase space, are the ones which spontaneously came out of water, right? 15 minutes ago. The very rare ones are the ones that we see where it's actually fully melted ice that melted into this state. So yes, there's these arguments from combinatorics, but you have to be very careful with them. And you have to remember, if you've not put in anything in your argument which specifies one direction in time over the other, you'd better not get out of your argument anything that specifies or prefers one direction in time over another. That was a long rant. That caused a lot of entropy.
Yeah, I'll admit to being puzzled by some of that.
I think with all the possible trajectories in the phase space, out of all the possible trajectories in the phase space, for most of those trajectories, the starting point would correspond to evenly distributed gas in the box. And the starting points of few of those trajectories would be those unlikely ones where you've got the gas in the corner of the box. That's why it's surprising. That's why it's surprising for us when you run things backwards and it goes into the corner of the box.
Yeah, so there's something called the recurrence relation. What that says is, if you have, again, gas in a box, if you wait long enough, take any point in phase space you like, right? There's a point over here which represents gas in half the box. Wait long enough, almost all systems will reach that state or get arbitrarily close to that state at some point. You might have to wait, you know, again, a squazillion times the age of the universe, but, you know, so for every point in phase space, you can say, look, at some point in the past or future of this trajectory, it was in that special half-filled box state. How long ago, or how far into the future is it? What's the time, you know, that you have to wait, you know, or you have to reverse backwards in time to get to the half-filled box state? What's remarkable about the ones we see around us, why we have a second law, is that for ours, that number is much, much less than the recurrence time, the squazillions of times the age of the universe. It's, you know, the ice was totally unmelted 15 minutes ago.
Yes, our universe is unique because our universe is 13.7 billion years, and it started it started from a point, presumably. So that's the unique thing about our universe.
Yeah, look, I think there's an interesting point there, again, related to what both of you said. As you said, if we could pick a random point in this phase space to describe, say, the distribution of all the gas in all the universe, etc., you would expect to pick a point where everything was essentially smoothly distributed, and essentially that what you've got is the maximal entropy state, right? Once everything's smoothly distributed, entropy is the biggest number it can be, and there's no energy differences, and so you can't do anything. But what Luke mentioned is that the start of our universe is weird. The start of our universe was like all the gases in one corner of the room. The start of the universe is not in that state where everything is spread out and at maximum entropy. It was actually at a low entropy state where everything was in the corner of the room. And there's a subtlety here to do with the fact that we've got to put gravity in as well. But that is one of the weird things about our universe. This thing called the past hypothesis, that our universe was born with low entropy, is really, really puzzling. Because people like Boltzmann and Kelvin thought about this a lot. And Boltzmann wondered if the universe was actually maximal entropy and we exist in a little fluctuation where you can get order forming, but that only exists for a short period of time. But because we know that our universe was born 14 billion years ago, that sort of option from Boltzmann is not really that credible. So we have to try and understand why our universe was born in this particularly ordered state, and we don't really have an answer for that.
Does that mean that because the universe started out from a special point in phase space, and really there's only been one trajectory because everything evolves in the way that it evolves, does that mean that we now have a sparsely populated phase space in all the places where the universe has been? And therefore, if you randomly pick a point in phase space, as you said, then you're more than likely to pick a point in phase space where the universe has never been and will never go, because the universe has a trajectory and it goes through phase space in a particular direction and order, because that's just what happens, because particles are exactly where they are, and the second law, Newton's second law, applies, and everything just goes where it's going to go. So do we have a sparsely populated phase space?
Well, we only have one universe, so it's a point in phase space. It's a very, very large.
I'm thinking about all the points it's been and
Yeah.
is going to go. Does that map out, trace out a sparsely populated phase space?
No, it's a large volume of phase space. It can be, in fact, it's immense. One of the most provocative scientific pictures I've ever seen was drawn by Nobel Prize winner Roger Penrose. And I can't remember which book this is in. Maybe The Emperor's New Mind.
I'm sure it's in this one.
Yeah, it is. Yeah, I've seen it. It's the one with it's a sort of a box. Yeah. I remember the diagram. Yeah.
And there is a white bloke with a long white beard reaching down and using a little pinprick to put the universe into this particular state at the start, right? Roger Penrose understands the past hypothesis that the state that the universe started off in is very, very unlikely if you take all the possible states. Luke, do you have the picture there?
I'll keep talking.
Okay.
I'm close. Oh, yeah, there we go.
Yeah, there we go. You know, so quite what Roger Penrose was hinting at there. You can read that yourself, but that is indicating that our universe started off in a strange state, and that strange state of low entropy, if we buy the entire entropy story, means that thermodynamics, the Industrial Revolution, the running of energy, and the melting of ice in my gin and tonic are related to the initial conditions of the universe, right? which I think is a kind of bizarre and strong statement.
Wow. Ian has his hand up. Ian, do you have something to ask or comment?
Oh, thank you. If I may. Yes, firstly, hello again, Luke Barnes. Remember Ian Bryce?
Oh, yeah. G'day, mate.
A long time ago, a debate. I think it might have been at Macquarie Uni on an interesting topic.
UTS, I think.
But back to the present. I'm interested in Geraint's illustration of two electrons coming together, and they reflect perfectly, and they come out again, perhaps at different angles, but at least with the same energy they went in at. If we enlarge that system to 3 electrons, so 1 electron comes into a system of 2, then we find statistically it's more likely that you won't get a single electron ejected again with high energy. You'll find that the energy gets averaged out among them. And the more electrons you have, the more likely it becomes that the energy becomes uniform. Or the same can be applied to gas molecules. So I think that illustrates the idea that the non-reversibility of thermodynamics applies only when you have something more basic than a simple system. And we know from the fundamental laws that if you've got a very simple system, then you can't tell if it runs forward or in reverse. But once you've got several particles there, and the more you have, the less likely that the molecules will accumulate in one corner of the room. So that's my understanding. And I'd like some comments on that.
That's not what Luke explained, I don't think, because if you have those 3 electrons now and you reverse the final trajectories of those 3 electrons to get them to come back again, what you will have is a collision similar to what you had before, and 1 electron will be ejected out with the higher energy. It will, in fact, be perfectly reversible, I think, if I understand what Luke described correctly. And it doesn't matter how many particles you have. If you reverse everything exactly, then you will get exactly the reverse, and you get back the previous state. Is that right, Luke?
Yeah. So to take the example of the ice in the glass. Well, all right, go on.
Sorry, Ian, go ahead.
Okay, a couple of things there. Quantum mechanics introduces a new variable where there's probability associated with their interactions. And I think that makes it even less likely that one will be spat out. But even according to deterministic physics, like billiard balls, I think you'll find that the probability that one will be ejected again at high speed goes down and down the more that you have, given that given all the states that the universe is really in, it's very, very, very unlikely to be in one of the states that ejects a particle at high speed again. I think that's the core of remember Maxwell's demon going back a long time? So that's my understanding. And not often we have such a brilliant panel to discuss such things. So I'm greatly enjoying it. Thank you, everyone.
So I'm going to jump in here and I think the argument is slightly incorrect. If you reverse things and you know things perfectly, it's perfectly deterministic in reverse, right? If you had a room full of gas and you knew where every atom was and you knew how fast it was moving, you wouldn't need notions of temperature and density and pressure. You just talk about what every single atom is doing and you could reverse all of them. But instead we talk about bulk quantities. As the number goes up, it's harder to do the sums, and it's easier to talk about the average energy involved rather than saying what every individual atom or electron or particle is doing. So I don't think it's just an issue of numbers, right? It's to do with the fact that, I mean, this is why statistical physics was invented, is that people felt that as we got to 2, 3, 4, 6, 10, a million, billion particles, we can't solve those equations. So we try and describe things in their bulk terms, and you end up with thermodynamics. But at the base
that's
level,
based on classical physics. Geraint, I understand. Once you bring in quantum mechanics, it destroys that traceability backwards.
No, quantum mechanics is deterministic and it's time reversible. Yes, it is. Quantum mechanics is deterministic. The the issue over the measurement, what happens when you do a measurement, that is not solved, and there are plenty of people who think that that too is deterministic and reversible, right? I mean, the entire basis of quantum computers being efficient is that they are reversible, right? So there is reversibility in quantum mechanics. It is messier, I'll give you that, but it doesn't move away from the fundamental laws that they are deterministic. The Schrodinger equation is deterministic. You reverse T, you can evolve your wave function backwards.
Scott, there are quite a few questions in the chat, so I don't know if you want to go through some of them.
Can I jump on one of them? The last one. Is there any universal benefit for entropy to exist? The answer is absolutely yes. In a second law world, in a world where there is a gradient of entropy, what that means is, well, perhaps it's easier to talk about the opposite. In a world which had reached maximum entropy, where there was no change in entropy, where the entropy yesterday is the same as today, is the same as tomorrow, that's a state of thermal equilibrium. And what that means is for every process in the universe, whether it is a microscopic one or whether it is a whole bunch of processes happening together, and we call that a macroscopic process, however you do this, whether it's one molecule of air bouncing off the side of my mug or the whole process of my mug cooling down to room temperature, in thermal equilibrium, on average, every process is matched by its time reverse. So for everything that happens in the universe, whether it's just a particle bouncing off or whether it's, T cooling down, its time reversal process happens just as often. What that means is, if you want anything in the universe to happen at all and not immediately be reversed by the reverse process, if you want anything at all to happen, it has to be a statistical fluctuation. If you're in thermal equilibrium, you have to just get very, very lucky. And the more things you need to happen, like something as large as, there's probably the number of atoms involved here is probably a number with about 23 digits in it, right? If you want that many, things to happen all in one direction by chance so that you get something like either the T heating up or the T cooling down or whatever, you're relying on extraordinarily rare statistical fluctuations. So in a universe where there's no, where entropy is maximum, where there's no change in entropy, every process is almost immediately erased by its opposite. Mm-hmm. If you want to do anything in the universe, in particular, if you want to lay down records, like memories, have anything that exists today be evidence of something that happened in the past at all, in any way, you'd better have a universe in which the second law operates, in which you have an entropy gradient. So on a very, very basic level, if you want anything to happen, you better have a universe in which the past hypothesis is true.
Okay, so it's useful in that sense. It's handy to have, so to speak. But how do we use it in physics? How do we calculate the entropy of a system? Or do we only calculate differences in entropy in systems? And how do we use it to manage whatever problem we're trying to solve? What is its application?
I'll mention one which is maybe one that people haven't thought about, right? And this is another definition of entropy that came around in the 1940s, and this is known as Shannon entropy. And Shannon was a communications engineer, and he was wondering about how much information can you encode in a message system if there's noise, right? So if you've got noise in the background, that noise interferes with your information. So how much information can you put in there? And he derived a formula for the entropy of the information, right? So, whether or not there was low entropy or high entropy in terms of how much information you could pick out from the signal. And it was kind of weird because the formula that he arrived at was the same as the formula for entropy as derived by a guy called Gibbs.
Mhm.
So Gibbs worked shortly after Boltzmann was working on entropy. He has got a slightly different formulation. They're related, they're subtly different, etc. Right? But one of the things that Shannon entropy suggested was that there was a link between information and order. And that's a kind of weird thing to sort of say, in that information is this fuzzy kind of thing. What is information, right? But then again, so is order. What the heck is order? And one of the places that this really struck me, and it still makes my head hurt to this day, right, is the question of, why does your computer get hot? Right? Your computer sits there, it takes in electricity and electrons move around and it does calculations. But why does your computer get hot? And of course, there is all the usual heating in there to do with the fact that you've got resistance and all that kind of stuff. But there's an aspect in there is that some of the calculations that your computer does loses information, right? So it's the equivalent of 3 + 2 = 5. Okay, so in the computer, there was something that knew there was a 3, something that knew there was a 2, and you add them together and the answer is a 5. But if I tell you that the answer is 5 and I ask you what were the numbers beforehand, you don't know if it was 3 and 2 or 1 and 4 or 5 and 0, etc. The computer had to forget. It had to forget some information. And that forgetting information, if you do the fundamental calculation, is related to the entropy increase, because there was a loss of energy, right, when we went from 2 bits of information to 1, and that is related to a limit. And Luke's gonna have to remind me what the limit's called. Oh my god, what's the limit of information called, Luke?
Well, what?
The limit of information, that log 2 thing, k log 2. Oh yeah, I've got it. Anyway, it doesn't really matter, right? But one of the reasons that your computer gets hot is because it has to forget things, right? And so there's a fundamental.
I wonder if the reason is the information leaving the computer and going outside the computer in the form of heat, so the universe is not forgetting? Is that the reason?
So that there's a lot of discussion about whether or not you can recover information from waste heat. And this is related to a bigger question of the information paradox of black holes.
Yeah.
Right? When black holes swallow things and they radiate that as gravitational waves, can you read the gravitational waves and work out the information of what fell in? But so one of the things that quantum computers want to do is they want their calculations to be fully reversible, because if you have a calculation which is fully reversible, then you don't have that thermodynamic limitation on that the computer has to forget, and therefore there's heat loss. So I think there's a fundamental thing right there, right? If you're sitting there with the laptop on your lap and it is getting hot and burning your thighs, part of the reason it's burning your thighs is that the chip is having to forget information to do calculations. And that's related to entropy increase.
And Richard Feynman actually wrote a book about this, and he was writing about reversible computers.
Yes.
And he was talking about these logic gates. So in a conventional computer, you've got an AND gate that has 2 inputs and 1 output, so you lose information. But the logic gates Richard Feynman was talking about is you have the same number of outputs as you do inputs. So you're not losing information.
Yeah, that's precisely right.
Yeah.
I'm going to have to change my answer to the initial question that Scott asked at the beginning of this session about my temperature going up every time I think of entropy. I think it's got to do with my forgetting things.
Well, that's an interesting question, right? Your brain runs on what is it? It's a few
20
watts.
About 20
watts. Yeah. So what is that energy being used, right? For what is it doing? And of course, there's the blood supply, blah, 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 blah. But some of it must go into, you know, the way information is passing around. And is some of the temperature from your head the fact that you're having to forget information? And I think it's possible.
In my case, definitely.
Yeah. Wear a hat.
All right.
I think it's I mean, we're celebrating Towel Day today, and a lot of the conversation we just had was, I don't know, resonated very strongly with the infinite improbability drive, not just in cups of tea driving it, but driving things which are extremely unlikely. I think that when they invented the infinite improbability drive, the physicists had a party trick at parties where they made all the particles in people's underwear jump 2 foot to the left, which is almost the same thing as particles in a box, but a little bit more interesting. Is there a length scale below which entropy doesn't work, or we can harness it differently than in sort of a macroscopic scale?
So the logic goes like this, as Geraint was saying. We start off in the Industrial Revolution, just thinking about how heat flows, even though we don't know what it is. We somehow, almost semi-miraculously, like wonderfully done, as I love that tinfoil hat, we find out that whenever there's a process that goes in one direction in time, but very rarely goes in the other, we can associate it with this property called entropy. We know how to calculate it, but what on earth is it? And then you have the idea of Boltzmann is, well, what entropy is, basically, is the volume, or is related to the volume of phase space that your system is, that the macroscopic state of your system is in. So think of, here's all of phase space, here's all the possibilities, and the gas is spread out all over the box state is almost all of phase space. And then tucked away tiny in a corner of phase space is all my particles are in half the box state. And so those sorts of states are rare, and the overall states, those are very much more common. If you have a very small system with not many particles, you have a very small phase space. So there's a point in which, when we use Boltzmann's ideas in the context of the past hypothesis to explain the second law, where we say, with a lot of particles, it is overwhelmingly probable that, and then we've sort of explained the second law. But down at a very small level, if you have a very small number of particles in the system, you have a very small phase space, suddenly, you know, those slightly weirdly, it's not as clear where the probabilities, the probabilities aren't sort of overwhelmingly this way rather than that way. They're a bit more evenly matched. So weirder things would happen, rarer things would happen more often, so to speak.
And can I, again, check in a point here? So as Luke said, volume over phase space is the thing we talk about. And it's one of the things that has always bothered me since I was a student, right? If you asked an individual atom in a gas, where in phase space is this distribution of gas? It's got no idea. It has no idea where the other gas particles are, what they're doing, and how they're moving, right? And so at some level, it's what we decided to characterize the gas as that has become this fundamental quantity that we talk about in terms of entropy and disorder. And in fact, it gets even worse. We talk about, in statistical physics, we talk about how we chop up the system. We talk about microstates, and often it's us that decides what the microstates are. Nature doesn't say to us, this is the way you should chop up a system. We decide that this is the way we're going to break things up, and we do our calculations from there. And sometimes you do wonder about, how does nature and entropy know what we decided in terms of chopping the system up? And again, I don't think there's a simple answer to how this works at a fundamental level.
You said that the electrons or the particles don't know about each other. Is that known? Or, you know, I mean, there are sort of, you know, quantum mechanical fields that, I mean, they diminish, but
Yeah.
that does it have a sense of all of the others? I mean, this goes back to the infinite improbability drive, where they go through every atom in the universe simultaneously. But is there a sense of that in reality?
I mean, a gas molecule only knows about its neighbors. It knows who it bumps into, right? So in this room, right, as Luke said, there is 10 to the 23 molecules in this room. This room is what, several meters across. And this molecule here, right, which is bouncing around, bouncing off its neighbors, it doesn't know what's going on to the molecule in the far corner of the room, right? They don't communicate with each other. There might be some macroscopic overall sort of things that we talk about, like pressure and temperature, etc., which gets communicated through. But this one here doesn't know what those guys are doing. So this one doesn't know where in phase space the description. For all it knew, it could all be in the corner of the room. It doesn't know that there's.
They're not entirely separate, Geraint, because each particle will carry with it, without knowing it, of course, will carry with it the legacy of its entire history. It'll be where it is because it was where it was, and it was somewhere else before that. And they're somehow all gravitationally connected. And so there's a whole history of how that particle got there. Does that have a role to play?
I don't think so, because it's Brownian motion, right? That it forgets very quickly. In this, look, if we reversed its motion, it could work its way backwards. But if instantaneously you said to this molecule, right, I'm looking at you, you're moving that way, I'd have to look at every other molecule to work out what its past history was. Sorry, we have a hand up.
Yeah, I just wanted to add a kind of philosophical thing here, because what Geraint is saying, in the history of philosophy, there's been a very long argument since the early Greeks about what we call external and internal relations, and so so Democritus and his atoms were these little inert, hard little particles, okay, that just simply moved around, that they had no other sort of properties other than their external properties. Opposite that was Parmenides, who saw the world as one big individual, and that if the separateness of things wasn't real, they were just ideals, so that we defined how we carved up nature. But the atoms that Dalton found, of course, and that we then kind of have elaborated for the last so many years, are quite different to the Democritean atoms, which were ideal. But in thermodynamics, aren't we working here with ideal gases? In other words, when particles move around, they move around without other sorts of properties, so that they wouldn't stick or they wouldn't change in any way by virtue of interacting, you see. So, so what we have in philosophy, you have a kind of general word of atomism. You also have what Russell and Wittgenstein came up with, which was logical atomism. And so I can give an argument that there's a philosophical background between the atomism of thermodynamics as the physical system, and then the logical atomism of the Shannon system. So, which gives an answer to why the two come again together. But in both cases, you have to have kind of ideal systems that ignores internal relations. So an internal relation is where individuals inhere in each other. External relations are only when the individuals are always inert and have no other internal properties where one thing affects the other. So when Geraint says this atom doesn't know what the other's doing, it is simply that it doesn't. There's nothing that, no property of the other is inhering in this one. So it is a kind of really, it's several thousand years old, these sort of arguments. My master's thesis in philosophy in Macquarie Uni, which was on mechanism, which was all about internal external relations with computationalism and with physics. So it's a very long argument, but I thought I'd add that in. That we're talking about ideal gases, aren't we, in this case?
I'm going to just put my hand up and just tell you that I've never had an original idea in my life, so I wasn't suggesting I was the first to think.
No, I wasn't saying you were.
And secondly, no, I don't think it has to be ideal gases, right? You can think of even non-ideal gases. We know that atoms only feel other atoms through electromagnetism, and we know that that's only felt over very short ranges through equivalently van der Waals forces. And so this atom here doesn't know what that atom over there is doing. I mean, I don't think it's that difficult to calculate.
So thank you very much, everyone. We'll call it a day there, but it to be continued. So thank you very much, and good night, everyone, and see you next time.